So good afternoon, everyone. I'm Amir Zamir, presenting Gibson Environment, Real-World Perception for Embodied Agents. This is work done at the Stanford and UC Berkeley with Fei Shah, Zhi-Yang, Alexander Sachs, Jitendra, Malik, and Silvio Savarese. So traditionally, computer vision is learned using data sets, but we need to develop perception models for agents that are physically active in the world, like robots. The conventional data sets are lacking for this purpose because they're obviously passive, so the camera location or content cannot change according to agent's actions. So you could learn perception with a physical agent in the physical world with an onboard camera. This approach has some drawbacks, like learning speed is bounded to real time, obviously, and important critical events like a car crash cannot be freely repeated, and working with robotic hardware is often time consuming. This has given rise to learning in simulation as an alternative approach. But using simulators often has the concern of generalization to real world. So focusing on vision, there are two main challenges about generalization from simulators. The first one is photorealism. So when you look at renderings coming from simulators, it's obvious that they are not coming from a real camera because they show some imperfections. But this potentially can be alleviated as computer graphics gets better and domain adaptation methods improve. A bigger issue is semantic distribution mismatch. So the models used in simulators are usually hand designed and artificial, so they do not really reflect the semantic complexity of real world. This is not an issue that can be improved or alleviated with any adaptation method. So we propose Gibson to get around some of these issues. So here's Gibson at a glance. There's a larger space. There's an active agent in it that can freely move around. The agent receives a stream of RGB frames as if it had an onboard camera and some additional modalities like semantics or depth. It's also subject to constraints of physics like gravity and collision. Here you can see, for instance, a Husky agent that is virtually driving around Stanford's Gates building. It hits the walls a few times and struggles, and ultimately it stops right here. All right, so here's some more details. So there are 572 buildings in Gibson's database. These are all real, full buildings. They are not synthetic, and they are scanned with 3D scanners. They can be explored in Gibson Simulator. On the right, you can see some random explorations, for instance. And you can import an arbitrary agent if you have its URDF. And the physics constraints are enforced by integrating PyBullet physics engine. Now, to provide that RGB frames from arbitrary viewpoints, we developed a novel neural network-based view synthesis engine. I'm sparing most of the details for the poster session, but it's faster than real time, and it has a baked-in mechanism for transferring to real world that we call goggles. Okay, so some more examples. On the left, you can see, for instance, a turtle bot that is going from living room to a bedroom that you can see right here. And on the right, you can see a Husky agent that is driving around the living room. And yeah, all right. So these are some sample perceptual agents that we developed in Gibson using reinforcement learning. On the left, you can see a car that is doing visual obstacle avoidance. On the right, you can see ant traveling down a stairway visually and some car traveling distant location. Yeah, this was an overview of Gibson Environment for learning perception based on virtualizing real world. You can access it from our website or GitHub.